Hello and welcome back students. In this video we are going to model a powertrain. The purpose of the powertrain modeling is to understand the data related to the batteries, motor parameters and the forces acting on the vehicle. So these are the outputs what we have got from powertrain modeling. The numbers of cells in the series and parallel which will be useful for designing the battery pack. Then to estimate how the resistive force are acting on the vehicle based on the input of our velocity profile. The variations of the wheel speed and the motor speed requirement are based on the effective gear ratios. For batteries, battery power requirements, battery current requirements, battery C rating, state of charge, how state of charge is remaining in our battery pack after one complete cycle. The battery capacity in ampere hours and watt hours. Here are the variations. If you see the variation of the wheel speed and the wheel torque for a given velocity input, this is the wheel speed and the torque required at wheel. So the torque required at the wheel is around 200 Newton meters. And the wheel speed is around 600 RPMs. After effective gear ratios, this is the speed and the torque which we require from our motor. So our motor should be capable of giving 50 Newton meter of torque, around 3800 RPM for a specified gear ratio. This is how the aerodynamic forces is according to the velocity profile input given to the vehicle, and this is the acceleration force. The velocity profile input given to our model is this, which we got from Optimum Lab, which you will be learning after in this course. So this is how the aerodynamic force is according to our input, as aerodynamic force is proportional to the square of the velocity. So it gives similar shape to the velocity profile input which we have given. This is the acceleration force. The force is negative, shows the strong deceleration. As you can see here, the speed has dropped from 50 to 30 kilometers per hour. There is a strong deceleration, and 60 to around 38 again there is a strong deceleration. So the values in the negative shows the strong deceleration and the positive values shows the strong acceleration. The gradient force is 0 as there is no slope, and the rolling resistance is constant as it does not depend on the velocity input, or we can say rolling resistance is independent of vehicle speed. This is the battery current which we require from the given input or the profile input. So it requires around 200 amperes of battery pack, and the battery C rate should be around 8C. The cell which we have used to estimate the battery C rate and the battery current is the Kokum cell, which is capable of 31 amperes and has continuous current of 8C, and maximum C rate is 15C, which nominal voltage is 3.6 volts. It is the same cell which we have modeled previously. The state of charge remaining after completing the complete cycle is around 96%. So 4% of the charge is used in one complete cycle. If we want to change the vehicle parameters like rolling resistance coefficient or the coefficient of drag, frontal area, gear ratios and others, so instead of opening every sub block and changing the parameters, we can easily change by going into modeling. Click on Model Explorer, Model Workspace, the powertrain model. Here we have already defined the parameters. So these are all the parameters like tire radius, gross vehicle mass, coefficient of rolling resistance, slope, frontal area, coefficient of drag, gear ratios, transmission efficiency. So we can easily change all the parameters from here initially from the source and run it again. So this makes the model more simple and easier to run every time. So to give the velocity profile input, which we have shown earlier from the optimum lab, which we have obtained like this profile. If you want to give input for model, first of all we have to obtain the data from this graph. For this, click on the add-on button, search for grab it and open the first one. I have already installed this, so I will open the folder, click on grabit.m and run that file. One window will open and you can load the image and you will load it and we will load it. This is the graph which we have obtained from our optimum lab. We have to calibrate the x and the y axis. So click on the origin of x axis, just click it and enter the value as 0. And the max value as x axis is 60. Click on the origin of y axis and give it 10 and max value which is 65. Once we have calibrated the x and the y axis, we have to grab the points. So click on grab points and start grabbing it. How many points we require, we can estimate that by clicking closer to it. So follow the profile and follow it, and here we can see the preview of how we are grabbing the data points. So after you complete whole profile, just click on grab point again, and here we can see the data which we have obtained. We can save it as mat file and also rename the file. So I have already obtained the data points and I have stored it as data 002 mat file. We have taken Formula Student Competition team data. When we talk about commercial vehicle, we can follow the standard profiles like FTP 75 or WLTC, etc. So I have one profile here in CSV format. So if you want to load this profile in our profile, so just double click on it and save it as a numeric matrix file and click on the import selection. So here we can see we have loaded FTP 75. In our model, go to from workspace block, put here FTP 75, click on apply and OK, and run the model. So I will click here. And we can see the value of 60 because our first profile was for 60 seconds, but this profile is for 1875 seconds. So to change the value, click on modeling, go to model explorer, model workspace, and change the time here to 1875 seconds. The profile limit is for 17.5. So just reinitialize from the source and we run it again. And here we can see the profiles, how the FTP 75 is. The wheel speed requirements, the wheel torque requirements, after certain gear reduction, the motor torque requirement and motor speed requirement from our motor or from your motor. And similarly, we can see the current variations, battery C rate requirements and motor power requirements. So to start the modeling, click on New button. First, we require from workspace block to input the velocity profile. We will name it as velocity profile input. Just double click on it and give it as data 002. Before modeling and other blocks, let's install the model parameters. Go to Untitled Model Workspace in Data Source, select MATLAB code. Here we will save our vehicle parameters and it will be easy for us to change it and run it according to our needs. First will be the radius of the vehicle, that is 0.254 in meters. Second, in gross vehicle mass, that is 330 kgs. Gross vehicle weight, which is a product of gross vehicle mass into 9.81 meters per second square. Then coefficient of rolling friction is CFR, that is 0.015. Next is slope of road, that is slope angle, that is 0 radian. Frontal area, that is AF, 1.1 meter square. The coefficient of drag, that is 0.4. Then the gear ratio, I am giving it as 6. Transmission efficiency, that is 90%, so 0.9. The motor efficiency, again 90%, that is 0.9. The motor controller efficiency, that is 0.95, that is 95%. Then battery voltage, that is 72 volts. The cell voltage of cokum cell, that is 3.6 volts, that is a nominal voltage. Cell capacity as it is 31 ampere hours. Lap distance, that is total lap distance, that is 0.787 meters, which we have obtained from Optimum Lab. Range required from our battery pack, so we require 20 kilometers range for a single charge. And the time to complete one lap as we obtain from Optimum Lap, which is 60 seconds. After we implement all the vehicle parameters, click on apply and reinitialize from source. So here we can see in our model workspace, we have opened the data, close it for now. We require one subsystem block and name it vehicle model. Double click on it. There is one input for our model, that is the velocity profile, and name it velocity profile in kmph. And the output which we have obtained in the vehicle wheel speed and the wheel torque required for a given velocity input. So hold the control key, click and drag it to copy the output port. We will name it wheel speed in terms of RPM and second in wheel torque in terms of Newton meter. As the velocity is in kilometers per hour, but we need meter per second, so add the gain block to convert it in gain block and divide the kmph velocity by 3.6 to convert it into meters per second. And name it kmph to mps. So to open the wheel speed and wheel torque, we need two subsystem block. Name the first one as wheel speed estimation and second one as wheel torque estimation. Double click on the wheel speed estimation and name the input port as velocity input and the output port and wheel speed in RPM. So the formula used for determining the wheel speed is velocity multiplied by 60 divided by 2 pi r. R is the radius of the wheel. So we have velocity, we required one constant block. So here we will give 2 pi into Rw, radius of the wheel, then the gain block to multiply by 60. And the divide block, and we will obtain our wheel speed in terms of RPM. So see the variation of speed according to the velocity profile input. So have the go to block and name it wheel speed. Keep tag visibility global because we will see all the output later. If it is a local, then we will be able to use the go to block in this wheel speed subsystem block only. Next is the wheel torque estimation. Now click on it. So here name it as velocity in meter per second. As the wheel torque is dependent on the force acting on the vehicle, so we need to determine all the forces acting on the vehicle, that is the aerodynamic force, rolling resistance force, gradient force and acceleration force, and multiply it with radius of the wheel to get the wheel torque. So for estimating the force acting on the vehicle, we need 4 subsystem block. So just hold the control key, click and drag it to copy all the blocks. And name it as rolling resistance force, gradient force, aerodynamic force and acceleration force. So open the rolling resistance force. The formula for estimation the rolling resistance force is F roll is equals to GVW into coefficient of rolling resistance into COS, that is the cos theta. Here the theta is in radian. And as it does not depends on the velocity, so delete the input port and insert the constant block by double clicking on the window. We require 3 constant block and copy it. First line is GVW, second is CRF, coefficient of rolling resistance. Insert the cos block. To open cos theta, and the product block give the number of input as 3. And just connect them, and here we will obtain our rolling resistance force. Here we will give one more go-to block to visualize the result as at last. Name it as rolling resistance and give tag visibility as global and apply it OK. Then go to gradient force. The formula for it is GVW multiplied by sine theta. Where the theta is in radian. So it does not depends on the velocity. Delete the input port. We require the constant block. We require 2 constant blocks, so just copy them. First is GVW and second is the slope, again angle multiply with sine theta. So insert the sine block and the product block. So here we will obtain the gradient force. Insert one more go-to block. Name it gradient force. Then go to aerodynamic force block. The formula is F arrow equals to half rho, that is the density of the air, into frontal area, into coefficient of drag, into square of velocity, which is in meter per second. Then we require 4 constant block. Copy the block. First is 0.5, second is RHO, that is the air density. So to add air density, go to Model Explorer, Model Workspace, and add air density equals to 1.225 kg per meter cube. Now click on Reinitialize from Source, close it. Go to Wheel Torque Estimation Aerodynamic Force, Air Density, then Frontal Area and Coefficient of Drag. Here we have to insert the square block for velocity square and the product block. Number of input as 5, connect them. This will be aerodynamic force. We need one go-to block and name it as aerodynamic force. Last is the acceleration force. The formula for acceleration force is GVM into derivative of velocity. Here is the velocity in meter per second. We require one constant block, that is GVM derivative block, and the product block. Here is the acceleration force. Insert go-to block and name it acceleration force. So we are with the forces and connect them with input of velocity. As we know, tractive force is the sum of all the forces, so we require add block. and number of input is 4, so list of sign is 4. Now connect all the forces to this add block. As we know that wheel torque is total tractive force multiplied by radius of wheel. So add one constant block, name it RW, one product block, and connect it to wheel torque. Give one go-to block to estimate the wheel torque. We are done with this model. Give them the velocity input and we will obtain the wheel speed and wheel torque. So after estimating the wheel speed and torque, and if we require how much torque is required from the motor, we require the transmission model. We need one more subsystem block. Name it as transmission model. Double click on it. So here we require two inputs, so copy one input. Name it as wheel speed and wheel torque. The output which we get from the model is the amount of speed and the torque required from the motor. So name it as motor speed and motor torque. The formula required for estimating the motor speed is product of wheel speed NW into gear ratio. And to estimate the motor torque, we have to divide the wheel torque by transmission efficiency multiplied by gear ratio. So insert one constant block, that is the gear ratio. product of having two inputs, and we get the motor speed. So add one go-to block and name it as motor speed. And to estimate the motor torque, we require transmission efficiency. So add one constant block. Double click on it and give it a name. Add product block to multiply the gear ratio and transmission efficiency, and one divide block, and we will get the motor torque. After one more go to block and name it as motor torque. We are done with the transmission model. Now we will connect the input. Next is to estimate the motor power required from motor. Add one subsystem block and name it as motor model. Double click on it. As there is a two input, copy the input port and name it as motor speed and motor torque. And the output will be motor power in terms of watt. So to estimate motor power, we require motor useful power, that is MUP. And then we will divide the motor useful power by motor efficiency to estimate the actual motor power requirement from battery pack. So motor useful power is product of 2 pi into motor speed into motor torque divided by 60. And motor actual power is motor useful power divided by motor efficiency. Add one constant block, that is 2 multiplied by pi divided by 60. Product block and number of input as 3. So once we have obtained the motor useful power, we want to derive the motor efficiency. Add one more constant block, that is motor efficiency, and one divide block, and then we get the motor power. So add one more go-to block to visualize the result and name it as motor power. So we are done with the motor model. So let us connect the inputs. Next thing is to estimate the battery parameters. We require one subsystem of battery and name it as battery model. To estimate the battery power requirements, so the formula is battery power is equals to the motor power divided by motor controller efficiency. As the motor power depends on torque. First, we have to take the positive value as motor power can also be a negative value, as our torque can be negative due to deceleration. So for estimating the motor power, we require the positive value. Insert one switch block. For the switch block, we will give the motor power input into this second input port. If the motor power is greater than 0, we will continue with the same motor power. If it is less than 0, we will give the output as 0. Add one more constant block and give the value 0 and connect. So once we get the motor power, add one more gain block to divide it by motor controller efficiency. Add one go-to block. So the output which we will getting in the battery power is in watts. So estimate the energy consumption per kilometer. We have to integrate the battery power and divide it by lap distance. We will get the motor battery consumption per kilometer, that is in watts per kilometer. So So the formula is watts per kilometer is integration of battery power divided by lap distance multiplied by 3.6 multiplied by 1000. So we require one integrator block. So give the input of the battery power to integrator block, add one gain block here, divide by 3.6 multiplied by 1000. That is the conversion of joules to watt hour. And again one gain block to divide by lap distance to get the watt hour per kilometer. Add one go to block, so the output we will get is watt hour per kilometer. So if we multiply the watt hour per kilometer, we will get the battery capacity in terms of watt hours. The battery capacity in watt hours equals the watt hours per kilometer multiplied by the range. Add one gain block, give the input of battery hours per kilometer and multiply by the range. So we get the battery capacity in watt hours. So once we get the battery capacity in watt hours, if we divide the battery capacity in watt hours by battery voltage, we get the battery capacity in ampere hours. So the battery capacity in amperes equals to the battery capacity in watts hour divided by battery voltage. At gain block, connect the battery capacity in watt hours divided by battery voltage. Add one go to block, name it as battery capacity in ampere hours. So once we get the battery capacity in ampere hours, we divide it by capacity or the cell capacity of a single cell. We get the number of cells in parallel, one more gain block, and divide by cell capacity. One more go to block and cell in parallel. Now to estimate the number of cells in series, we need to divide the battery voltage by cell voltage. So add one constant block, that is the battery voltage, add one gain block to divide it by cell voltage. So here we get the cells in series. Now to estimate the battery current, we have to divide the battery power by battery voltage. So add one gain block, one divide by battery voltage. Add one go to block. Here we will get the battery current. Once we get the battery current, so if we divide by the battery capacity in ampere hours, we will get the battery C rate. So add one constant block, and here we will name it as battery capacity in ampere hours. We have to change this value. Once we run it, we get the battery capacity in ampere hours. So just flip the block and add one divide block again, flip this block and connect the input. Multiplication port will be connected to the battery current as it has to be divided by battery capacity in ampere hours. Add one go to block to estimate the battery C rate. Again flip this block, connect it. And this is the battery C rate. Now in order to estimate the state of charge, we will insert one more subsystem block and name it as SOC. Just open it. The formula for estimating the SOC at time t is SOC at time t minus 1 plus or minus integration of current with respect to the time divided by the cell battery capacity in ampere hours multiplied by 3600. Here the plus sign is used for charging and minus sign is used for discharging. So here we require two input battery capacity and current. Name it as current and battery capacity in ampere hours. Add one gain block to multiply the battery capacity with 3600. And one integrator block and one divide block. So we have estimated this integration part. Initially we are consuming at time 0, our SOC is 100%. So add one constant block and keep the value 1 as it is 100%. And add one subtract block to subtract the value to connect it to the positive and the integration to the negative. Add one gain block to convert this decimal to percentage, so multiply by 100. And here we will get the SOC, so add one go to block for visualizing the SOC. There is no output from the SOC, so just delete the output port. Just connect the input, so current and battery capacity. So we are almost done with the powertrain modeling and we are left with the visualization of the results. So add the from block and here click on the updates and insert the number of cells in series. Just copy this block and change it to number of cells in parallel. To visualize the result, we require a display block. Just connect them. Now to visualize the forces acting on the vehicle, insert the from block. As there are 4 forces, so just copy and copy the from block and name it as acceleration force. Next is aerodynamic force. Next is rolling resistance force. And the last one is gradient force. Add one scope block for displaying the graphs. Double click on the scope block, go to the settings, give number of inputs as 4 and change the layout as 2 by 2 matrix. Apply and close it. Connect the ports. Name the signal as acceleration force, aerodynamic force, rolling resistance force and gradient force. So to estimate the wheel speed, wheel torque, motor speed, motor torque and the block again, we require 4 blocks and name it wheel speed, wheel torque, motor speed, motor torque. Copy this scope block and connect the blocks as well as the signals. We have to estimate the battery parameters. Again, insert the from block and give name motor power. Copy the block and change it to the battery power. Again, copy the block and change it to the battery current. Copy the block and change it to the battery C rate. Copy the block and name it as SOC. Insert the scope block. Go to settings and change the number of inputs as 5 and matrix. Name the signal as motor power in watts. Battery power in watts. Battery current in amperes. Battery C rate and change and state of charge. Now we are left with the estimation of the battery capacity in ampere hours and watt hours. So add from block, name it as battery capacity in ampere hours. Copy the block and change it to the battery capacity in watt hours. Again copy the block and change it to watt hours per kilometer. We require the display block and connect them. So we are done with the powertrain modeling. Go to simulation and change the stop time to time required to complete one lap. So we have name it as time while we save the values. So just give the stop time as time and click on the run button. Here we have obtained the battery capacity as 29.36. So open this model and change the capacity to 29.36 and run this model. So this is what we have seen, like the battery current required is around 200 amperes. The battery power is 16 kilowatts. The motor power consumption is around 16 kilowatts. But here we can see the negative values. This negative values can be used for regeneration, but as we are not using this regeneration model in state of charge, you can see there is no upgrade, there is downgrade. So after one complete cycle it is consuming 4% charge, and we have the rest 96% of state of charge SOC. And the battery C rate required is around 7.5 C discharge. Then the wheel speed required is around 600 rpm, and the wheel torque required is around 200 Newton meters. After gear reduction we required 15 Newton meters and around 3800 rpm from our motors. So our motor should be capable of delivering 50 Newton meter at 3800 rpms. This is the force variation, this is the acceleration variation. As the negative value denotes the strong deceleration, the aerodynamic force variation, which is similar to the velocity profile input which we have given, as it depends on the velocity. Rolling resistance remains constant as it does not depends on velocity, and the gradient force is 0 as there is no slope. Thank you very much.